Okay, ladies and gentlemen, I hope you can hear me well. All right, if you have any questions, you can raise your hand and stop. And that's also very easy chapter. Why? Because students have difficulty when actually they face problems. That problems means word problems. You need to read and use a suitable variable to denote the unknown and form your equation. That is the most challenging part. Understanding the problem is the biggest challenge for students. But here, most of the questions are like equation type questions. That's why it doesn't take much time. You'll go a bit faster, okay? So you need to practice all the questions. So we will start. What we have here, we have indices here, solving exponential equations, surds, and logarithms. Today, we will talk about these two things, indices and the solving exponential equations, okay? Maybe tomorrow, we will talk about surds and logarithms. And next week, maybe one session, if you have questions, I'll try to answer those questions, or we'll do some revision and finish this chapter. Okay. All right. So if A is positive number, here actually this is our A, okay, positive number, we have A times A times A equals A cubed. So here A is called the base and 3 is the index or exponent or power. So actually here we are talking about if N is positive integer, the positive integer, this positive integer means we are talking about these numbers. 1, 2, 3, 4, 5, right? Dot, dots. All right. And in math, a lot of times we may face the product of something by itself many times. One example is this, right? For example, let's say 2 times 2 times 2, okay? And mathematicians thought, okay, a lot of times we are facing such things, they actually feel the kind of need to introduce new notation. And they introduced this exponential notation. Okay, so in a compact form, how can we describe this multiplication? So they introduced this exponent or index. We can just write it as 2, and here we just write 3. That is 2 to the power 3. That means that this 2 is multiplied by itself 3 times. Okay, like 3 times 3 times 3 times 3 times 3. And also in a compact form, how can I describe this? Using this definition, that is 3 to the power 5. That is a bit smaller one. It is indexed, right? We call this superscript notation. And if it is here, we call this subscript notation. Okay? So here we are using superscript notation to describe the power of a number. All right? So in general, what is our definition? We are defining that here, if A is positive number, here if A is positive number, and N is positive integer, all right, and also it can be 0, but we'll talk about this later. So this A to the power N is defined as A times A times A dot dot dot. Here we have A. How many times is it multiplied by itself? N times. Okay, that is our definition. All the rules we are going to talk about, actually, it is based on this definition. Okay, and that is index, or this one is exponent or power, right? So this one is base. How do you read this? It is 4 nth power of A, or A to the power N. Okay. All right. Now we will see some properties. Using those definition, we can have this property. Properties are some small theorems or rules. It says that if m and n are integers. Now here we are not saying positive integers, any integer. So when we say integers, these are integers, right? This is z. Let's say let's denote the set of integers by z, and these are dot dot dot. Here we have -3, -2, -1, 0, 1, 2. These are the integers. Integer means the fraction part is 0. So these are the property. The first one is a to the power m times a to the power n is equal to a to the power m plus n, right? And actually here, we have all these properties here, a to the power m. For example, if you just prove the first one, y a to the power m times a to the power n equals a to the power m plus n. And by using the definition, the first one, for example, here, right? For example, the first one, a to the power m times a to the power n. And by definition, this one, what does this a to the power m mean? That means that this a is multiplied by itself m times, right? Times, here we have a to the power n. Again, by this definition, this a is multiplied by itself n times. Now, all our multiplication here I have m a's, here we have n a's. Now, if you count together, how many, by using the counting principle, how many a's we have? Here we have m plus n, right? Here, if I have 7, here we have 5, altogether 12. If we have 10, here we have 5, altogether 15. So again, by using definition then, since here m plus n a's are multiplied by each other, using this definition, I can write it as a to the power m plus n, right? In similar way, also for division, you can prove that. For example, the second thing says that if a to the power m is divided by a to the power n, that's equal to a to the power m minus n, right? Why is it so? Because if you just write this, that is, here we have a times a dot dot a. How many a's we have? Here we have m a's. And here we have a times a dot dot a. How many a's we have? N a's. Now, if you just cancel out, right? Let's say here we have m and n a's just cancel out. How many left then? Here we have m minus n. Here we have, for example, 10 a's, 10 to the power 10, 8 to the power 10. Here we have 7 a's. So 7 of them, we cancel each other. How many left here? 3, right? That is 10 minus 7. Okay. So using these two, again, also this one is a to the power m to the power n. For example, C, how can we do that? Again, using the definition a to the power m to the power n means here we have a to the power m times a to the power m times a to the power m. How many a to the power m's we have? Again, we are using definition n, right? So that's equal to, if it is n, now I can just write it as a to the power, here we have m, right? And here we have n. Okay, because here I just need to write something that put here n, right? And also if the base is the same, here we have a to the power m, b to the power m, but here exponents are the same. So we can just write it under the same exponent, this m. So we can just write it as a times b to the power m. And also for division, similar thing. And here, y a to the power 0 equals 1. A lot of students may confuse about this, okay? And we can just prove it like this. What does this a to the power 0? I'm just going to prove like this. Here we have a to the power 0. I can write it as a to the power m minus m. What is m minus m? Is equal to 0. And using this property, right? So this a to the power m minus n, something, is equal to this. So I can write it as a to the power m over a to the power m, because these things are the same. And we know that in real number system, if you divide any number by itself, of course, except for 0, that is equal to 1. That's why a to the power 0 is equal to 1. Okay, anything to the power 0 is equal to 1, except for 0. Of course, here a is not equal to 0. That's why we say here a is not equal to 0. 2 to the power 0, 1. Negative 1 to the power 0, 1. Negative 1 over 2 to the power 0, 1. 1 million to the power 0 is equal to 1. And how about this important property, a to the power minus n equals 1 over n. Let me just prove this in another page. Okay, before we continue this, general form is a to the power minus n. I can write it as a to the power 0 minus n. Using the division rule, I can write it as a to the power 0 over a to the power n. And what is a to the power 0? Is equal to 1 over a to the power n. And that's why a to the power minus n equals 1 over a to the power n. How about general form? If you're given as a fraction a over b, and here we have to the power n, let's say minus n, a over b to the power minus n, that is equal to a over b to the power 0 minus n, that's equal to a over b to the power 0 over a over b to the power n, which is equal to, this thing is 0, right? And using the third property, I can write it as a to the power n over b to the power n, and it goes up, right? Sorry, this thing is 1. So here we have b to the power n over a to the power n. Exponents are the same, so I can write it as b over a to the power n. Okay, for now, that's all. So if we just consider these examples,
Hello, mày cái bông bự nhạc thơ nè
Caro chưa?
đang nè bà bông
continue. A, yeah, somebody is speaking out there. A, simplify each of the following. How do you simplify this? The first one, 27, and this is 3. And we know that 27, I can write it as 3 cubed, right? So I can write it as 3 cubed to the power 1 over 2 times, here we have 3 to the power 1 over 2, which is equal to, here we have 3 to the power 3 times 1 over 2. It is 3 over 2 times 3 to the power 1 over 2. And using that property, we can write it as 3 over 2 plus 1 over 2. What is it? 1.5 times half. That's equal to 2. That's equal to 9. And also another way we can solve this, that's one way of solving this problem. Another problem is here B, 32, 16. Now from here we can see that I can write the 32 as the power of 2. And also 16 as the power of 2, right? And what is 32? That is 2 to the power 5. And 16, 2 to the power 4. So if you substitute here, we have 2 to the power 5. Outside the brackets, here we have 3 over 5 divided by 2 to the power 4 and to the power 1 over 4, which is equal to, remove the brackets, here we have m times n, right? 5 times 3 over 5, that's equal to 3, is divided by 4 times 1 over 4, that's equal to 1. We don't have to write 1. And it is divided. It is divided, right? So here we have 2 to the power. Here we have 1. 3 minus 1, which is equal to 2 squared. That's equal to 4. Okay. And how about the last example? C, 2 to the power negative 3 times, here we have 16. We know that we can write it as 2 to the power 4. And outside the brackets, here we have 3 over 4. First, we need to remove the brackets. Here we have 2 to the power minus 3 times 2 to the power 4 times 3 over 4. That's equal to 3. And the 2 to the power 2 to the power, here we have negative 3 plus 3, that's equal to 0. And we know that 2 to the power anything, that's equal to 1. Okay? More examples. Simplify each of the following. Let's start with A. Okay. Here, by using this property, here we have mth root of a to the power n. Yeah, this line, why? N is defined as a to the power n over m, right? Here we know that n is positive. To do this one in A, third root of a, right, or cube root of a, I can write it as a to the power 1 over 3, because I have to change this third into index form first, and divided by, here we have a fifth root of a squared. So that is a to the power 2 over 5. And times a to the power, remove the brackets, negative 1 times half, that's equal to negative half, right? Now we have to simplify this. To do this one, that's equal to a to the power divided here. So 1 over 3 minus 2 over 5. And here we have times, so here we have plus negative half, which is equal to, I can do calculation here. What is it? 1 over 3. 1 over 3 minus 2 over 5. And the minus 0.5, that's equal to minus 17 over 30. So that's equal to a to the power minus 17 over 30. Okay, simplified. So another example, B, how about here? Here we have 12, here we have 6, here we have 8. And I can only write it as 2 to the power of something, 3 to the power of something, because this 12 is 3 times 4, this 6 is 2 times 3, and 8 is just 2 cubed, right? The first thing, this 12, I can write it as 2 squared times 3, right? 4 times 3 equals 12. And here we have also the bracket 2x plus 3 times, here we have 2 times 3, 2 times 3 to the power x minus 5, right? And this 8 is 2 cubed to the power 2x minus 1. Now if you remove the brackets, here we have 2 times this, right? 2 times 2x, it is 4x plus 2 times 3, it is 6 times, now here we have 3, and it is just 1. I just write this exponent here, 2x plus 3 times this thing, 2 to the power x minus 5 times 3 to the power x minus 5 times, how about here, 2 to the power 3 times 2x, 6x, 3 times negative 1 minus 1. Sorry, 3 times negative 1, it is 3. Right. So now here we have the base 2, here we have 2, here we have 2, here we have 2, right? So that thing is, here we have equals 2 to the power. Here we have 4x plus 6, 4x plus 6, all are multiplied. So plus x minus 5, plus x minus 5, plus 6x minus 3, times, here we have 3, right? 2x plus 3, 2x plus 3, and here we have x minus 5, x minus 5. X minus 5. Okay, that's all I think, because here we have the base 3 here, only 2 multiplicants, right? Now we need to simplify. Here we have 2 y 2, 4x plus x, 5x plus 6x, that is 11x. 6 plus negative 5, it is 1. 1 plus negative 3, it is negative 2, minus 2. Times, here we have 3. 2x plus x, 3x. 3 plus negative 5, minus 2. Okay, so we have simplified. Another example, this C. Here we have something, here we have, actually this is 81, 9, all base, here we have 3, and 27. We know that here 81 equals 3 to the power 4, and 9 equals 3 squared, and 3 equals 3 to the power 1, and 27 equals 3 cubed, right? So if I just substitute here, what we get here? C, let me change my marker color here, let's use green. Here I have 3 to the power 4. So here we have 3 to the power 4 to the power x plus 1. X plus 1. Minus 3 squared to the power 2x plus 1. Over, here we have 3 to the power x minus 4 times 3 cubed, and to the power, here we have x plus 2. X plus 2 equals, okay. Here first, if you remove the brackets, here we have 3 to the power 4 times x. 4x plus 4 times 1, it is 4. Minus 3 to the power 2 times 2x, it is 4x. 2 times 1, here we have 2, right? And here we have 3 to the power x minus 4 times 3 to the power 3 times x, 3x, and 3 times 2, it is 6, right? Equals, I can simplify this also, this x minus 1, 4, 3x plus 6, right? And the sum is, here if we just write here, x minus 4 plus, what we have here, 3x plus 6. 3x plus 6. X plus 3x, 4x, and the negative 4 plus 6 is equal to 2. So here we have 3 to the power 4x plus 2. And here we have 3 to the power 4x, 3 to the power 4x, okay? Let me just take them out. So here we have 3 to the power 4x times, what do we have here? 3 to the power 4 minus, here we have 3 squared. Over, if I take this here, 3 to the power 4x out, right? And what is that here? 3 squared. 3 squared. Equals, these two things cancel each other. Even here, 3 squared is a common factor. 3 squared. What is that here? 3 squared minus 1 over 3 squared, right? And also these two things cancel each other, common factors. And the 3 squared is 9. 9 minus 1 is 8. So this thing is equal to 8. Okay? All right. Another example. Here it says if y equals 2x to the power x, express each of the following in terms of y. And this method is a very useful method to solve exponential equations. Sometimes if your exponential equation is very complicated, by introducing new variable, we call this auxiliary variable in math. All right, that is auxiliary variable. Because already in the equation, x is the variable, right? We are introducing another one so that I can change or describe this equation in simpler form, so that we can solve this much faster and making less mistakes. Okay, so here, if we introduce this variable, y equals to the power x, in question A, I can write this as 2 to the power x times 2 squared minus 2 to the power x times 2 to the power negative 1, right? And what we have here, 2 to the power x, 2 to the power x is a common factor. Take this out. So 2 squared is 4 minus 2 to the power negative 1. It is 1 over 2. And here we have 2 to the power x, which is equal to 4 minus half. It is 3.5. That is 7 over 2. And what is 2 to the power x? It is y. So that's equal to y. So we have expressed the given expression in terms of y. If y is equal to the power x. Question B, here we can write it as, I'm just using the property that a to the power m plus n is equal to a to the power m times a to the power n, right? Here it is minus. So here we have 2 to the power x times 2 to the power 1. When it is 1, we don't have to write it. Plus, here I can write it as 2 squared, right? Because 4 is 2 squared. Here we have x minus 1 minus 2 cubed to the power. Here we have x plus 2 equals. Now let's remove the brackets first. Here we have 2 times 2 to the power x, because a times b equals b times a, plus here I have 2 to the power 2 times x, 2x, or can I just, anyway, okay, times 2 to the power 2 times negative 1, negative 2, minus 2 to the power 3 times x, 3x, 3 times 2, it is 6, right? Or I can separate this. Here we have times 2 to the power 3 times 2, it is 6, right? Now I can just rewrite this as 2 times 2 to the power x plus this thing is 2 to the power negative 2 times 2 to the power x to the power 2, because 2 times x equals 2x, minus this thing is not x squared. We should multiply this also when it's outside the bracket, right? So be careful with this. 2 to the power 6, I can write it as 2 to the power x to the power 3. So now if we just make our substitution and we denoted this 2 to the power x by y, so that thing is y and that is y and y. What do we have here? 2 times y plus 2 to the power negative 2, 1 over 4 y squared, right? Y squared minus 2 to the power 6, that is 64 y cubed. So we have expressed the given expression in terms of y if y is given by this 2 to the power x. Okay. Guys, now we'll talk about solving exponential equations. All right. So we have about 10 minutes left. No problem. So an equation that contains an unknown in an index form or index or exponent is called an exponential equation. Okay, when we say equation, we know that in math, we claim that one sentence or statement is equal to another statement. Then we try to find under what conditions these two things are equal. But here, that equation, the statement or that expression, if it involves any exponential expression and in the equation, then we say that it is exponential equation. Okay, some examples for exponential equation. For example, 2 to the power x is equal to 3. Exponential equation. 2 times 3 to the power x minus 3x squared, for example, equals 7. All right. Another example, 2 over 7 to the power x is equal to 5. These are some examples for exponential equations. But here to solve this exponential equation, we will use this technique now. Okay, later you will see that without introducing logarithm, we are not able to solve exponential equation. But here in this part, we are going to consider some simple equations. So in general, we shall use the following rule to solve exponential equations. If a to the power x equals a to the power y, then x equals y, where a is positive and a is not equal to 1. Okay. Now what happens if a is equal to 1? Then we have to consider this separately. Okay. All right. In general, we will consider this kind of examples. That means that if you are given exponential equation, we have to bring this into this form. Then from here, we will form another equation so that this x equals y. We may have some kind of expression here, also expression here, and they just solve this equation. And we know how to solve linear equation or algebraic equation, right? Let's start with some simple examples. In A, for example, here 4 to the power x equals 8, right? Okay, 4 to the power x equals 8. The question is, what must be the value of x so that when I raise this 4 to the power x, it must produce 8? That's the question. To do this one, I try to bring this into this form. A to the power x equals a to the power y. Now, if you look at the basis, this 4, I can write it as a power of 2. This 8, I can write it as a power of 2. So here we have 2 to the power 2 or 2 squared x, that's equal to 2 cubed, right? From here, if you remove the brackets, 2 times x, 2x equals 3. Because now, from here, we can form equivalent equation, right? For this equation to be true, this thing should be true. So if you solve this here, what is x? X equals 3 over 10. Another example, B, okay. 4 to the power x plus 1 is equal to 0.25. Right. So here we have 4. I can write it as a power of 4, so we don't have to write it as a power of 10. What is 0.25? 0.25 equals 1 over 4, or I can write it as 4 to the power negative 1, right? So what do we have here? Here we have 4 to the power x plus 1. On the right hand side, 4 to the power negative 1. So as you see here, now again it's in this form, right? So bases are equal and it is non-negative, right? So for this equation to be true, their indices must be equal to each other. So we get equivalent equation here, x plus 1 should be equal to negative 1. So solving this linear equation, we get x equals negative 2. Okay. The last example for today. Okay, so something is missing here. Let me. All right. Okay, another exponential equation, the last example for today, and we will continue from where we stop tomorrow. Okay, solve the equation by using the substitution of y equals to the power x. Okay, if y equals to the power x, all right, first I try to write everything here in terms of to the power x. The first thing here is we can write it as 2 cubed times to the power x squared, right? If you simplify this, here we have 3, right? 3 times x plus 3. Not 3, it is 2. 2 times x plus 3. 2 times x plus 3. Plus, second thing is I can write it as 2 cubed times 2 to the power x equals 1 plus 2 to the power x. Now we will make our substitution here. 2 cubed is 8. 2 to the power x is y. Here we have squared plus 2 to the power 3. It is 8. Here we have y equals 1 plus 2 to the power x is y, right? And what we get here is just quadratic equation, right? So here take everything to the left hand side. Here we have 8y squared. 8y minus y, it is plus 7y, and 1 to the left, it is negative 1 equals 0. Why it draws this line? Okay, so now we need to solve this quadratic equation. How can we solve this? First attempt, let's try factorization methods. So here we have 8, here we have 1. This, I think, just the cross multiply gives 7, so I can write it as 8y times y. The thing is 1, 1, so it is plus, I should put minus here. 8y times y, 8y squared, negative 1 times 1, negative 1. When you cross multiply, right, 8y plus negative y is equal to 7y. So we can factorize it as 8y minus 1, and y plus 1 is equal to 0. Okay? So from here, y is equal to 1 over 8, or y equals negative 1. Equals negative 1. And from here, positive number to the power something, it is always positive. It's always positive. That's why actually this answer is rejected. It's never equal to negative number. Rejected. So the answer is 1 over 8. So here, if we substitute here, let's say this one is first step, this one is second step, and the third step is here. So y is equal to the power x equals 1 over 8. What is 1 over 8? It is 2 to the power minus 3. So from here, dots, 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 the solution of this equation is negative 3. So if you substitute negative 3 for x in this equation and evaluate this and also evaluate this expression, left hand side will be equal to right hand side. Okay? Guys, that much is enough for today. Okay, tomorrow we will continue. Now I will share this chapter 10 worksheets with you. Okay, you should practice those questions. All right, I think we have 2 more weeks, 3 weeks left. It's about 6 hours. And after that, you have final exam. As you know, all final exam will come from chapter 8, 9, 10, and 11. Thank you very much. See you tomorrow. Bye-bye.